All right, welcome to day 42. Today, we're going to demystify the one concept that really truly taught computers how to see. We're talking about the convolutional neural network, or CNN. So let's start with a really basic question. How can a small child look at a picture and, without any effort, say cat, when for decades, getting a supercomputer to do the same thing was an almost impossible challenge? What's the secret that we have that machines just couldn't figure out? Well, the answer wasn't just about raw computing power. It was about a completely different way of thinking. And by the end of this, you're going to understand the core brain-inspired logic that finally cracked the code for computer vision. So where did this breakthrough idea come from? Well, instead of trying to brute force the problem, researchers took a step back and looked at the one system that does this perfectly, our own brain. You see, when you look at a cat, your brain doesn't just process the whole image at once. It's a hierarchy. First, your visual cortex picks up on really simple things, little lines, curves, edges, bits of color. Then it starts piecing those together into more complex shapes, like an ear or a whisker, and only then does it assemble all of that into the final concept of cat. A CNN is built to copy that exact process. It uses layers to build up understanding, starting with the simplest patterns and working its way up. So how does it see those first simple patterns? Well, imagine you have a tiny magnifying glass, and instead of looking at the whole picture, you slide this little lens over every single part of the image. But you're not looking for a cat, you're only looking for one thing, maybe a simple vertical edge. In a CNN, this little magnifying glass is called a filter, and the network has tons of them, each one designed to hunt for one specific simple pattern. Okay, so now that we have the core idea, let's look at the actual engineering components. What's in the toolkit for building one of these digital eyes? The heart of the whole operation is the convolutional layer. This is the real workhorse. Its job is to take all those different filters we just talked about, the edge detectors, the curve detectors, and slide them across the input image. Here's how it works. The layer takes a filter, say one that looks for horizontal lines, and places it over a tiny patch of the image. It does a quick calculation to see how well that patch matches the filter. If it's a strong match, it puts a high value in a new grid called a feature map. Then it just slides the filter over one spot and does it again and again until it has scanned the entire image, creating a complete map that shows exactly where all the horizontal lines are. Now, right after that happens, the network does something simple but really important. It applies a function called ReLU. All you need to know is that this step allows the network to learn more complex relationships. Without it, it could only learn simple, linear patterns. With it, it can start to understand things like a whisker is a line next to a nose shape. It's a critical little tweak. Okay, next up is the pooling layer. So after the network has created all these super detailed feature maps, it kind of needs to zoom out and get the general gist. Pooling helps it do that by shrinking the map down. It basically summarizes small neighborhoods of pixels into a single pixel. The most popular way to do this is with something called max pooling. It's super simple. It just looks at a little 2x2 square of pixels and keeps the biggest number, the brightest spot. This does two great things. It makes the network way faster, and it also helps it recognize an object even if it's moved around a bit in the frame. So after a few rounds of convolution and pooling, the network has built up a really rich set of features. Now it's time for the final verdict. That happens in the fully connected layer. This layer takes all that high-level information, the ears, the whiskers, the fur texture, and weighs it all to make a final call. It's the part that says, okay, given everything I've seen, I'm 85% sure this is a cat. So this all sounds pretty clever in theory, but where do you actually see this stuff in action? The answer is pretty much everywhere. Seriously, you're using CNNs every single day. They're what unlock your phone with your face. They're what automatically tag your friends in photos. Self-driving cars rely on them to see the road, pedestrians, and other vehicles. And in medicine, they're becoming absolutely vital, helping doctors spot tumors in scans much earlier than the human eye ever could. So when you boil it all down, CNNs work by teaching a computer to see the world like we do, by starting with simple patterns and building them up, layer by layer, into complex objects. And the key takeaway from all of this is a really powerful idea. To solve a massively complex visual problem, you don't attack it head-on. You first teach the system to get really, really good at seeing the simple things